Let's start with a common situation in pharmaceutical analysis. You run your HPLC method, expecting the usual chromatogram, but suddenly, a new peak appears that wasn't there before. At that moment, several questions arise. What is this impurity? Where did it come from? Is it harmful, and can it affect the quality of the drug? Unknown impurity identification is essentially scientific detective work. In this presentation, we'll walk through the practical workflow used in pharmaceutical laboratories to detect, analyze, isolate, and ultimately identify unknown impurities. Unknown impurities are not just analytical curiosities, they are a major regulatory and safety concern. Guidelines from regulatory bodies such as ICH and FDA require that impurities above certain thresholds, typically around 0.1 to 0.15%, must be identified and characterized. This is important for several reasons. Impurities may introduce toxicity risks, including potential genotoxic effects. They may also indicate degradation pathways, which can impact the stability of the product over time. Most importantly, impurities can affect the efficacy and overall performance of the active pharmaceutical ingredient, or API. The first step in impurity identification is detection, and this usually happens during routine HPLC or UPLC analysis. Analysts may notice a new peak, a shoulder peak, or sometimes a peak whose area increases in stability samples. But before assuming it is a real impurity, we must verify a few things. Is the peak reproducible across injections? Could it be an analytical artifact, such as contamination or instrument noise? Only after confirming that the peak consistently appears, do we proceed to investigate it as a true unknown impurity. Once the impurity is confirmed, the next step is to gather initial structural clues, and one of the most powerful tools for this is LC, MS, or liquid chromatography coupled with mass spectrometry. LC, MS helps determine the molecular weight of the impurity and provides valuable fragmentation information. For example, a mass shift of plus 16 Daltons often suggests an oxidation reaction. Fragmentation patterns can reveal functional groups, while isotope patterns may confirm the elemental composition. These insights allow scientists to begin forming possible structural hypotheses. After obtaining mass data, the next step is to understand where the impurity might originate. Impurities typically fall into three broad categories. They may be process-related impurities, coming from starting materials, reagents, or catalysts used in synthesis. They can also arise from side reactions, where unintended chemical transformations occur during the reaction process. Finally, some impurities are degradation products, formed due to factors such as heat, light, moisture, or changes in pH. Understanding the synthetic pathway often provides strong clues about the likely structure of the impurity. Once we have a hypothesis about the impurity, we need to isolate it for detailed analysis. The challenge is that impurities are usually present at very low concentrations, sometimes less than 0.1%. To obtain enough material, scientists typically use preparative HPLC, which scales up the separation process. During this step, the impurity peak is collected through fraction collection, allowing analysts to gather purified material while ensuring the integrity of the sample is maintained during isolation. With the impurity isolated, we move to the most important stage, structural confirmation. The gold standard technique here is nuclear magnetic resonance spectroscopy, or NMR. Proton and carbon NMR provide information about the chemical environments of hydrogen and carbon atoms, while two-dimensional NMR techniques reveal how atoms are connected within the molecule. High-resolution mass spectrometry further confirms the exact molecular formula. Together, these techniques allow scientists to determine the complete molecular structure of the impurity. Even after identifying a likely structure, scientists perform one final confirmation step. This often involves synthesizing the suspected impurity and then spiking it into the sample. If the synthetic compound shows the same HPLC retention time, the same mass spectrum, and the same NMR characteristics, the match confirms the impurity's identity. At this point, the investigation moves from hypothesis to definitive proof, which is essential for regulatory documentation. Let's summarize the overall workflow for unknown impurity identification. First, the impurity is detected as a new peak during HPLC or UPLC analysis. Next, it is analyzed using LC-MS to determine its molecular mass and obtain structural clues. Then the impurity is isolated using preparative HPLC so that sufficient material can be collected. Finally, the structure is confirmed using techniques such as NMR and spiking experiments. This systematic approach ensures accurate and reliable impurity characterization. In pharmaceutical analysis, an unexpected peak is not necessarily a problem. It is an opportunity to deepen scientific understanding. By carefully identifying and characterizing impurities, scientists ensure that medicines remain safe, stable, and effective for patients. So the next time you see an unknown peak in your chromatogram, don't panic. Instead, think of it as the beginning of a scientific investigation, where careful analysis and the right tools can reveal the complete story behind that mysterious peak.